Nice introduction. And I'm approving the recording. Okay. Yeah, thank you. Thank you for the introduction. Thank you also for the opportunity to speak. Yeah, if there's questions throughout, feel free to put them in the chat. I won't be able to see them myself on my laptop screen here, but you know, if there's something urgent, feel free. And otherwise, we'll do questions at the end. So what I want to do in this talk is explore a kind of fairly new area in machine learning that deals actually with old problems. But if you think about the systems that we use machine learning for, like these systems like search engines, recommender systems, all the systems in e-commerce, I think we've come to realize that these systems are not just systems that make predictions, but that these systems are actually taking autonomous action in the world. And more we're seeing that we're not just using these kind of autonomously kind of made decisions in the online world, but it's more and more moving towards consequential decisions that mediate many of the institutions in our society. So what I want to explore today in this talk is the problem of learning from past actions. And in particular, in these online systems, we have these logs of past actions, interaction logs, where the system took an action, and we see what the effect is of this action on the world. And of course, we gather a lot of this type of interaction log data, and it's very useful. We can use it to measure and optimize the performance of these systems. That's actually the main source of knowledge for many of these systems, like the recommender systems. Never seen a movie. All that it knows is how it interacted with users in the past. And we can use it for personalization. Okay, so what do I mean with these systems taking actions? Let me give you a couple of examples. First example would be maybe a news recommender, like this app here. It has like this For You spot. It can put one news story there. And so the way you can formalize this is that there is some context X, and the context would be maybe your user profile. Then there's a set of actions that the system can take, maybe all the available news stories of that day. And it has to pick one to place into that spot. And then it can measure the effect. Well, do you read it or do you not read it, right? And what the system wants to do, it wants to kind of bring you stories that you want to read. You want to maximize the effect. Or even further, I mean, the same system. Now you've decided on a particular news story. There's more decisions to be made. Like the context now would be, here's a user and a particular content, a particular story that you put in there. But how do you actually display that content? So for example, you have multiple images that you can pick from, or multiple headlines that describe the same news article. For different people, there may be interest in different aspects of that story, and you want to make a selection there. And again, you have to take an action. You have to pick a particular heading to put there, and you see the effect, the click or no click. And you want to optimize this. And maybe the final example is your voice assistant. And so the context here would be, you're telling Alexa, Alexa, play music, which hopefully didn't set up a whole lot of Alexas in your houses now. The action that Alexa can take is that, it has to pick one playlist or one album, depending on that customer. And the effect is, how long does that customer actually listen? That's the measurable effect. The actual effect is how much does the customer enjoy that music. But it's, again, the system takes an action autonomously, and we can observe the effect and want to maximize the benefit. And of course, there are many other examples like that. But at the high level, they all have kind of the same structure. They have this contextual bandit structure. Namely that a context comes in, an existing system, which we call pi null in this talk, picked an action in the past. And we can now kind of, for that particular action, we see the reward or loss, depending on how you think about it, it's just a number, right? That this action incurred. Now, we see this for the past system that ran. And so the data that we get is kind of biased by that past system, right? We see the rewards for the action that the system picked in the past. But the goal of learning is to come up with an improved system, right? A new system, pi, that selects actions that are even better, that optimize rewards. So this is what this talk is about. It's about this problem of batch learning from bandit feedback. And let me put this into perspective of kind of a normal taxonomy of learning problems. We have full information learning where somebody gives us a label saying, this is the correct label for this image. This is full information. All the other labels are incorrect. So we know for every possible label the reward, basically. And we can do this in the batch setting. We have tons of algorithms for that. And we can do this in the online setting where we don't have a kind of an existing batch of data, but we are kind of gathering our data as we go along. But we don't have full information. We have partial information. We have this bandit data here, right? We only see the reward for a particular action that we actually picked in the past. And in the online setting, we have algorithms for that as well, EXP3, UCB1, are some of the classics, right? But what we want to do now here is that, right? We want to use past interaction logs, which are logs of bandit feedback, and we want to do batch learning with them, right? We don't want to have the system interact with the user like in this kind of very interactive way. We just want to use the log data. And the reason for that is clear, right? We already have this data. It's there. We should be able to exploit it. Okay, so we'll start with kind of formalizing the problem of batch learning from bandit feedback, and then think about how could we actually approach this. So the way to formalize the problem is to maybe think about it in analogy to a problem that we already know quite well. And so in an online system, we have contact, action, and effect. And the same type of structure we also have in medical decision making. So for example, the context there would be a patient described by age, lab results, and so on. Then the action that we take for that patient depends on the context, and it's the treatment that we give, maybe a particular drug or the surgery, right? And we pick we can only pick one treatment for each patient. And for that particular treatment, we see the outcome, let's say measured as survival time. But we don't get to see what would have happened if we had taken a different action. So we're dealing with factual outcomes. Factual outcomes are the ones for the action that we did actually take. But we also have to reason about counterfactual outcomes. What would have happened if we had taken a different action? And so structurally, these two problems, our online system problems and like how to kind of inform medical decision making and picking the right treatments there, structurally, they're actually the same from a statistical perspective. So what we're going to do is we're going to borrow a lot of kind of the conceptual setup that kind of come out of causal inference and controlled randomized trials, and think how we can kind of translate them into our types of learning problems. So in particular, everything is going to be kind of set in the potential outcomes model. This idea that you have factual outcomes, these are the outcomes for the action that we did take, and counterfactual outcomes, the actions that we could have taken where we don't know the reward. So I've already mentioned that we have these systems, I called it pi. Let's actually call this a policy. And a policy is just a kind of a mapping that given an action, given a context X, picks an action A. And as will become clear throughout this talk, it's a good idea to think about these policies as stochastic mappings. So that means a policy is just a conditional probability distribution where we condition on the context, and then we pick the actions from, stochastically. And so the way that I'm gonna, and of course, this is just a, stochastic policies are greatly, strictly more expressive than deterministic policies. You can just emulate a deterministic policy by putting all the probability mass on a single action. So the way that I'm going to visualize this in this talk is that, let's say for a given context, this is my space of action. This box is all the actions that I can take. Normally they're going to be discrete, but discrete actions are difficult to visualize. So let's think about this box as all the actions that we could take. And then two different policies, pi1 and pi2, basically are just two different probability distributions in this space. So maybe pi1 picks actions more preferentially from here, and pi2 picks actions more preferentially from here. So how do we measure the quality of a policy? Well, I mean, I already said that before. The most natural thing would be to take the expected reward. We can take other measures as well, but let's stick with expected reward because it's the most tractable one. But you can, I'll briefly at the end of the talk also allude to like additional criteria, like fairness criteria, or certain constraints that you want to put on your policies that you can estimate, have as additional kind of objectives as well. So the expected reward is basically just that, we have a context distribution P of X, and we just assume that our contexts come in IID, just in regular supervised learning. Then we have our policy that picks actions conditioned on the context, and then we observe the reward. And for now, I'm sweeping under the rug that the reward can be stochastic, nothing changes, just simplifies the notation to make it deterministic here. Okay. So the reward, this is just the expected reward under the context and action distribution. And again, if you visualize this, you can think about, I've shaded in the colors here. Green are good actions, high reward or good reward. Red are bad actions, bad reward. And so this policy pi1 for this context is mostly red, so doesn't pick good actions. Pi2 is mostly green, picks better actions, so higher expected reward. I'll also call this utility as a shortcut for expected reward. So now how do we estimate the quality of a policy? How do we estimate utility? And the gold standard that's used in industry, and certainly also in controlled randomized trials in medicine, is that we actually field the policy, right? That we do an A/B test. And so what this means is that we take the policy, and now we apply it to our context distribution. And what we may get is something like this here, right? We now pick actions. Let's say we see this context multiple times. Normally it doesn't happen, but just for visualization purposes. And we see there's a bunch of red actions, green actions. And if we want an estimate of utility, because we're sampling from the right distribution, we can just average the rewards. And that's going to be an unbiased estimate of our utility. And so that's a very straightforward way of getting utility. It's also consistent, it's unbiased, it's very nice. But it has a problem. The problem is that if you want to run an online A/B test, we really have to kind of get all of these policies implemented and get it in front of users in our case. And that's problematic for multiple reasons. First, we actually have to productionize each of these policies. That means we have to make sure it's completely bug-free, it fulfills the latency requirements, it fits into our operational system. From an engineering perspective, that takes weeks. And then we have to gather data from this policy. And again, that is something that takes on the order of weeks. So conducting one of these online A/B tests is a matter of weeks, if not months. So the number of these tests that we can make is really limited. And it's a lot of work. So what we would really like is, we would like to do these kind of not online A/B tests, but offline A/B tests, and get these counterfactual estimates that tell us maybe if we just have, if we have a lot of data that's already lying around that we have from some existing policy, that's our log data from last month, can't we just use that data to come up with an estimate of how well would some other policy, let's say Pi 6, have done if we had used it instead of the policy Pi null that actually collected the data? And so if we were able to do that, we could do these offline A/B tests, in minutes or seconds, right? There's no productionizing, there's no getting new data, that takes time. And we can do it, for many, many different policies. And so there would be, we could do that at a much higher rate. And we could do a lot of offline testing before we actually put something into online production, which comes with its own risk, right? If you put a bad policy online, that's a high cost. So so we would like to do this offline A/B test, these counterfactual estimates. How well would a different policy have done if we had used it in the past? But what's the problem with that? Why is this hard? Well, the problem is that we don't actually know the utility of every possible action that we could have taken. But what we do only know is we know the utilities at these points of, these are the actions that the logging policy Pi null has taken in the past. But now our new policy that we want to evaluate, this Pi here, may pick different actions. And what are we going to do if it picks an action that we don't actually know the reward for, right? If you want to evaluate this expected reward here, the utility, there's lots of actions that we don't know the reward for. So kind of the problem is that there is a mismatch here in this expectation between policy that collected the data and the policy that we want to evaluate, right? We need to kind of swap this out. Okay, so how can we get around this problem of missing rewards for many of the actions? Well, the first idea that comes to mind is, well, we know machine learning, we know how to predict. Let's just build a reward predictor. So what we could do is we could take all of our observed rewards. We know for context X and action A1, we got that reward. And for context X, we got that reward, right? So we have basically supervised data for this learning task of context action mapped to reward. And we can treat this as a regression problem. Just have to come up with a nice kind of set of features that describe the relationship between context and action. And then hopefully we can learn a good regressor for the rewards. And if we have a regressor for the rewards, this delta hat here, we can just impute, right? And whenever we don't know we haven't actually observed the reward, we just plug in our imputed reward and we can compute this expected utility. Now so conceptually what we're doing is we have these observations in this feature space, two features here, psi1 and psi2. Reds and the greens, good and bad actions. We learn a reward predictor, fill in the whole space. But the issue now is that it's complicated to get this reward predictor right. And in particular, we need to really think about how it extrapolates. Often we don't have observations in big parts of the space because our logging policy picked only certain actions, not other actions. So if we now want to evaluate an unobserved action that's maybe here, we're probably pretty good. But if we're using this reward predictor to now ask, ooh, what's the best action I could take in this context? Then what it will do is it will pick that action down in the corner here. That's the greenest action, right, according to our reward predictor, but we have very little data. And it really matters where the greenest action is based on how our model extrapolates beyond the observed data. So that can work, but it can also go wrong in a sense that we can have a very biased estimate. And bias is something that's hard to detect, right? If you actually want to estimate bias, bias is the deviation between the expectation and the true value. You actually have to know the true value. And we don't know the true value. That's the whole point, right? So bias is difficult to elicit. And so, it's hard to tell when this works and when it doesn't work. So lots of people have, there's a lot of the big history of building click predictors, for example, for search engines, but it's a hard problem. So can we avoid this hard problem? And so what I want to do in this talk is I want to approach this problem in a fundamentally different way. And instead of estimating rewards, I want to go more directly for estimating utility, skipping this step of reward prediction. There's also a conceptual issue there. Christian mentioned Vapnik, right? What Vapnik always says is, if you want to solve a statistical problem, don't first solve a harder statistical problem and then dumb it down. But reward prediction is basically doing that, right? We're first solving this really hard problem of predicting the reward everywhere. And then we're using the results of that to estimate reward. Can we just do this kind of end to end, skipping that hard problem? And the answer is that we actually can. So the idea is that instead of, so as I mentioned before, right, the key problem is that we have to change between one probability distribution to another, right? The logging distribution, pi null, and the new policy, pi. And we can do this directly through this technique that's called inverse propensity score weighting, or IPS weighting. And there's a very simple estimator, this IPS estimator, that is directly an unbiased estimate of the reward of the policy, or of the utility of the policy. And all that it does is it takes the observed rewards and re-weights them by this ratio of what's the probability under the target policy that we want to estimate the reward for, and the policy that actually collected the data, the pi null, and the probability of the action that we took under the logging policy. That's what we call the propensity, and I'll typically call it small p in this talk. So why does this work? What's the intuition for why should this work? So let's say we have gathered our data here. We're not filling in the whole background with color. We just know the dots here. And now we want to evaluate this policy here. Now there's a mismatch in distribution. We can't just average. If we just wanted to evaluate the utility of pi null, then yeah, that would be easy. That would be just pi null here and pi null down here. That always cancels to 1. And we would have the online estimate, just average the reward. But now these probabilities are different. And what this IPS weighting does is it says, oh, maybe, if the probability under the logging policy was higher than under the target policy, let's say for this point, then we downweight it. The logging policy kind of picked it too often. And the target policy that we want to estimate picked it less often. So every time we observe it, we divide it by a certain factor, right? And in expectation, that gets us right. Or here, this action, under the logging policy, it was picked too infrequently. So every time we do pick it, or we do see it, we upweight it so that it's appropriate for that new policy that we want to evaluate. And that's exactly what this IPS weighting does. And it does it in a way that you get an unbiased estimate. Key point here is that the logging policy has to have full support. That means it has to have non-zero probability for all actions that the target policy has non-zero probability for as well. Okay, so now we have a tool, this estimator, this IPS estimator, that directly lets us estimate utility of some other policy, even though this policy did not gather the data itself. Now, it's an unbiased estimate of quote unquote error, right? Just like we have in supervised learning typically. So what we can do is we can do empirical risk minimization now. And our training error measure is not the number of errors or whatever you want to typically pick in supervised learning, but it's the IPS estimate. Same thing, unbiased estimate of the performance. So basically what this means is if we have some log data and we have some space of policies that we want to pick the best policy from, what we can do is we just pick the policy that has the best training error. Or here the highest training reward, same thing, according to the IPS estimate. So that seems straightforward, but that can go wrong as well. Why can this go wrong? Well, this is the example from the previous slide, right? We have so we have now a whole space of policies. We evaluate every policy in the policy space, pick the one that has the highest estimate reward. When we do that, for this policy pi1 here, that's pretty close to the target policy here, to the logging policy. You know, we upweight these points here, but there's a whole bunch of points that we can kind of draw upon. But in that policy space, there's probably also a policy that's really far away. And so what this means is that the probability distributions are very different. And up here, we only have a single observation. And that observation through this inverse propensity score weighting here, this importance weight, gets huge weight. So we still have an unbiased estimate, but we have an unbiased estimate that basically depends on only a single data point. So it's really easy to overfit. So one thing that's happening here is that for different policies in our policy space that we're now optimizing over, the variance of the quote unquote training error can be quite different. And that's something we don't have in supervised learning. Supervised learning, like for every rule in our part of the space, the training error estimate has about the same variance. Not the case here. The further the policy is away from the logging policy, the smaller the effective sample size and the higher the variance. So that's something we have to control for. And if you actually do the learning theory behind it, you will see that generalization error bounds, you get generalization error bounds that say something like that. If you want to get a bound on the true utility, then you look at the utility on the training set. That's our IPS estimator, for example. But now you also have to account for the variance of this estimate. And the variance of this estimate can now be different across different policies. And you still need to do the normal overfitting control for capacity. Right. And so this bound here now accounts for the this fact that the variance can be different for different policies. Now, as typically in learning theory, the bounds are very loose, right? So you have to take them with a grain of salt, but they typically tell you what you should be optimizing. So what you can derive from or take away from this bound is that what you want to optimize is an objective that optimizes training performance, controls for kind of capacity through regularization. But it has this additional term where you also want to kind of regularize for the variance. And so now you have basically two regularizers. And you have two regularization constants that you need to tune. That is lambda1 here for the variance regularizer. Make sure that the policies kind of stay close to the logging policy so the variance doesn't blow up. And then here lambda2 for the overfitting control. And we call this counterfactual risk minimization in analogies to structural risk minimization, because we now have these two regularizers that we're controlling. So how can we take this and turn it into algorithms? So the first algorithm that I want to introduce is called POEM, for policy optimizer of exponential models. And basically the only thing that's left is, we have the objective already that was on the previous slide. We just have to come up with a policy class, and ideally one that's semi-tractable to optimize, right? So, and a very tractable one, a very nice one, is to pick these softmax policies. And it's basically the same form as a conditional random field or a structural SVM. where you have some joint feature map between the input X, the context X, and the action A. That gives you a feature vector, and then you just learn a weight vector. And it's a softmax in the sense that you're exponentiating this, and then you're just normalizing so it sums up to 1. It's nicely differentiable, and we use these types of functions all the time. But now it's a policy, right? It's a function for picking actions, not for modeling conditional. It's not for modeling conditional class membership or something like that. So, okay, now let's take this policy, type of policy, and plug it into our objective, which is, what we had on the previous slide. And it's differentiable, so you can do gradient descent on it. And if you apply a couple of tricks, like a majorization, minorization trick, then you can even do stochastic gradient descent on it. So how does this work now? Let me just give you a couple of examples in terms of empirical results. So first one is a synthetic example where we've taken a standard text classification data set, the Reuters data set, where we have the contexts here are now documents, and we're synthetically generating bandit feedback from the label vector. It's a multi-label problem. We are taking 4 of the labels. So is it about a corporate acquisition? Yes or no. Is it an earning report? Yes or no. And there are 4 of those. So we predict there's a label vector now. And now the way that we're generating bandit feedback is we take one of these contexts, which is a document. We have a logging policy that we've trained. And now we make this stochastic that now predicts a label vector. So for example, we pick this. Now that logging policy picks a label vector. So for example, here it says 1, 0, 1, 0. So the first label is attached, second isn't, third one is attached, fourth one is not. And it's stochastic, and it picks this label with probability 0.3. And it happens to draw that one. And we record the propensity, this 0.3 probability under the logging policy. And now we observe the reward. And the observed reward here is 2. So 2 of the labels are correct, but we don't know which ones. And that's how we're generating more and more bandit feedback. And so that's obviously much weaker feedback than somebody telling us, oh, this is the correct label feedback. This is the correct set of labels. But can we still learn, even despite this weaker bandit feedback, the kind of correct classification policy? And the result is on the bottom left here. The top here is the performance of the logging policy pi null. So it's pretty bad. It has a high Hamming loss towards the correct label vector. Down here, this is if you train a conditional random field on the full information labels. So this is kind of how good we could hope to get. And this is the amount of bandit feedback that we give to poem. And as you can tell, if you give it more and more bandit feedback, it does converge to the kind of skyline, right? Eventually, despite the fact that each of these kind of pieces of feedback is less informative, if you give it enough, it eventually converges to the skyline performance. So this was synthetic. We also worked with a media company from New York that wants to remain unnamed, and actually getting this in production. And these types of methods are now used in industry quite extensively. So the problem that they had was they have some query coming in, and then they had a set of answer templates that were kind of conditioned on that query X, context X. But you had to still kind of pick the right answer template from that set. And what they wanted to optimize their utility metric was, how often they picked the correct one minus how often they picked an incorrect one. And they also had abstentions, which would be a 0. They already had an existing system where they actually had hand-labeled data, where they had human assessors saying, oh, for this query X here, this was the correct answer template. But they only had like a very limited amount because it's very difficult to label this. There's also conceptually, it's a problem because the assessors don't always know what the correct answer is, or many of the queries are ambiguous. Anyway, so they trained a logistic regression scorer, this kind of form here, just to predict what the correct answer template is. And what they had used in production was that they would pick the answer that has the highest score according to the logistic regression model. Now, they wanted to improve on that because they knew they had limited data and the data was probably not the correct data just because the assessor didn't know how to label. So they collected bandit feedback by taking that policy that they had from the logistic regression scorer and made it stochastic. Instead of picking the argmax, they picked the softmax. And in the soft of the score, and in the softmax, you can use this kind of temperature parameter lambda here to tweak how random you want to make the logging policy. If you set lambda to 0, you get the uniform policy that just picks actions uniformly at random. It's probably not what you want, but then you increase lambda to make it more deterministic. And so they picked a level of stochasticity that they were comfortable with, and that gives you enough exploration of the action space to do this IPS-based learning from. And then they kind of observed user feedback, or derived it from the actions of the user, how often where they got the answer right or wrong. And so they had this now logged, propensity scored log data. And they trained POEM, and they actually saw a very large improvement. So for kind of in terms of kind of improvements in these online systems, 30% is huge. Okay. Now the question that you probably have is, oh, can you do that with deep learning too? And so let me address that as well. The answer is, it's actually really straightforward. Instead of picking a softmax of a kind of linear model, you can just pick a softmax of a deep network, right? Most of the deep networks have at the end a softmax layer anyway. So it's not much change. Just the objective change. The IPS objective is different from a typical kind of cross-entropy objective. So you just take that policy class, stick it in this counterfactual risk minimization objective. Now, truth be told, there's an additional problem that comes up when you have a deep network. It's a very high capacity model. There's a whole kind of new way of overfitting, which we call propensity overfitting. But it's something that you can control with a different estimator. It's called a self-normalized estimator. But in principle, you can do the same thing that we've done before. And you just, the optimization becomes a little bit more tricky, but you can reformulate this problem, break it down into a couple of sequential problems that you can all solve with stochastic gradient descent, and then assemble a solution afterwards. So does this actually work? So we've done this on an image, an object recognition task on the CIFAR 10 image collection, just as a proof of concept. The type of model deep learning model that we used was a ResNet 20. And the way that we generated bandit feedback for the CIFAR 10 data set is we picked an image, that's our context. Then we picked an action from a logging policy that was stochastic. And then, so picked an image here, a cat. Our logging policy picks an action, says it's a dog, picks that, let's say, with 30% again. And then we observe the loss here, and it says, that was wrong. But it doesn't tell us that it's actually a cat, right? So we only get this partial information data again. But again, if you give BanditNet, this is what we call this method, enough bandit feedback of this type, you see that with more and more feedback, the test error rate decreases, and it eventually converges to a ResNet 20 that was trained with the full information feedback. So again, if, you converge to a performance that is kind of the skyline of what you could expect. So these were two problems of contextual bandit learning. Let me briefly also talk about other partial information learning problems, because I think we have these in many different variations. And so one that I think comes up very often as well is actually the problem of learning to rank, where the actions that we take is, presenting a ranking. How do we deal with that? So what we have there is, we have log data where, we have some query distribution coming in, our P of X distribution. We have a deployed ranker, pi null, that most cases now is deterministic, actually. It takes in a query and then it spits out a particular ranking, and it's deterministic. It always spits out the same ranking for that query, although you could change that as well. And then we observe the clicks, right? Maybe a click on position 1 or position 4 here, and we want to then train a new ranker, pi, that ideally does better than the ranker that generated the click data, the log data. So conceptually, that seems similar, right? Again, we have actions that the system takes, and we get partial information, but it's slightly different. So in particular, it's different in the sense that even for the action that we present, we don't observe the full reward. But we have combinatorial actions where we observe the reward on pieces of that combinatorial actions on individual documents. So let me illustrate the problem with this example here. So we have a deployed ranker that maybe presents this ranking. And now we have a different ranker that presents this ranking. And let's just be the simplest problem. We just want to decide which of the two rankings is better. Now, if we have fully labeled data, full information data, we would know for every document here whether it was relevant or not. And then evaluating and deciding which of the two rankings is better is just a matter of picking a metric and then computing the metric. So let's pick a very simple metric just to keep it simple for this talk. The rank of the relevant documents. It's something that we want to minimize. So here the rank of the relevant documents is 3, 6, and 7. So the sum of those is 16. And here the sum of the relevant documents is 7. So ranking to the right is better according to this metric. And it's easy to compute, right? We know the relevances of all the documents. But now let's think about what we have when we have click data. When we have click data, what we maybe observe is, that left-hand ranking got shown to the user, and the user clicked on result number 3. So what we can probably deduce is that, result 1 and 2 were probably not relevant. 3 was relevant. Let's say click means relevance, and we can be more sophisticated there. But what we really don't know is these documents down here, D, E, F, and G. Did the user not like them, or did the user just not see them? And now if we want to evaluate this ranking, and these documents, these yellow documents are now at the top, what are we going to do with them, right? We just don't know. We don't have the information. We don't know the relevance of these documents. And if we're naive about it, we would conclude the wrong thing. We would conclude that, this ranking on the right is worse than the ranking on the left, which is not true, right? And again, we're dealing with missing information. We're dealing with counterfactuals, right? We're dealing with the counterfactual of what if we had presented this ranking instead of that ranking? Would the user have been better served? So deterministically, I think we're stuck. we just can't decide for these two rankings. But in expectation, we can use the same tricks that we've used for contextual bandits, just in different disguise. So in particular, let me formalize this a little bit more. We have a loss function, maybe the average rank of the relevant documents. And there are some true relevance labels, but we don't know them. If we had them, we could compute our loss. And that's this delta here. So this is just the average, the rank of the relevant documents. We make the following two assumptions. The first assumption, we'll assume that if a document is clicked, then the user must have looked at it and found it relevant. And vice versa, if the user looks at something and finds it relevant, then the user will click on it. So that's probably fairly reasonable as an approximation. What's our problem here from the previous slide? The problem is, if we don't see a click, it could have two causes, right? One cause is the user didn't see it, wasn't observed. This is this O here. Or the user didn't find it relevant, but we don't know which of the two it is, right? We can't tell it apart deterministically. But again, we don't have to tell it apart deterministically. We can just tell it apart in expectation. So if we know the probability with which a user looks at each position in the ranking here for this particular ranking A that was presented, we can again use this as a propensity to use inverse propensity scoring. And in particular, we can use this inverse propensity score estimator, which is again an unbiased estimator of that true ranking metric that we want to evaluate. And again, the intuition is actually pretty simple. It says that if we know that only half of our users kind of find this document, the probability is a half. If that's in this particular position in this particular ranking, then every time we see a click on C, we upweight it by a factor of 2, right? So we're kind of making up for the fact that we're missing half of our data. Or down here, we know that only 20% go down to this position here for this particular ranking. So every time we do see a click on F, we upweight it by a factor of 5. And that makes up for the missing data, right? For that we only see 20% of the data. So in expectation, we are now doing the right thing. And that gives us an unbiased estimate. And if you have an unbiased estimate for each ranking, right, then that is very high variance. But if you now average over many queries, the law of large numbers kicks in again, and we get a consistent estimator of the true ranking measure. And we can then do, again, learning to rank via risk minimization, and we'll get a consistent learning process under the usual assumptions. The two things that we still have to kind of figure out is how do we actually optimize this in a practical algorithm? How do we solve this argmin or argmax, depending on whether minimizing or maximizing? And how do we define a propensity model? First one is easy. Actually, if you take an existing learning to rank algorithm, and I've just done it here for a propensity-weighted SVM rank, it's typically very easy to build in. If you know ranking SVM, you recognize it. If you don't know it, I'm not going to explain it. But really, the only thing that's different is that I put a 1/Q in here, which is this probability of observation. It's just a constant that gets stuck in here. The rest stays exactly the same. The theory stays the same. Everything stays the same. And if you want to do this with deep networks as a ranking scorer, you can do that as well. So then the second problem is that, how do we define these propensities, these observation propensities? And the simplest model for that is to use a position-based model, where you are basically just saying, there's a kind of constant probability across all queries that, a certain percentage, Q3 of our users go to position 3, and a certain percentage of our users go to position 6. And it only depends on position. And that is something you can actually estimate remotely via like kind of swap experiments, or you can exploit A/B test data that you have, and you make it more conditional on context. So there's a lot of different ways how we can estimate these propensity models. So just one quick result. So here is simulated click data for the Yahoo Learning to Rank standard benchmark. Lower is good in terms of performance. This is the number of click training examples based on clicks. And this is the logging policy that presented the rankings during logging. This is the best performance that we can hope for again. And if you do the kind of propensity weighted learning to rank, again, you get convergence to the Skyline performance. This green line is if you ignore the position bias, if you ignore the cues, and you get a biased learner. And no matter how much data you throw at it, it's optimizing a biased objective. It's not going to be consistent. All right, so I've focused on optimizing utility, and I've these two applications, the contextual bandits and the learning to rank. But the same techniques actually apply to a big range of other kind of problems that you may want to, or other objectives that you may want to optimize. So in particular, in the last few years, I've become more interested in also guaranteeing certain fairness objectives. But the same techniques like IPS weighting, debiasing for selection bias also apply to these other objectives that you may want to have in your system as well. And so they're kind of generally useful for any objective that you may have. All right, with that, I want to conclude. So maybe the takeaways is that many systems that we have are really systems that are about taking actions, making interventions in the world, and then trying to optimize the effect of these interventions. Whenever you have that, the data that you have is partial. You only get to see the factual outcomes, what you actually did. You don't get to see the counterfactual outcomes. What would have happened if you had done something else? And you have to deal with that. And I think the kind of this causal inference approach in this talk is an interesting way to doing this. Gives you the possibility to offline evaluation in terms of offline A/B tests, and also to do learning. If you're interested in digging in a little bit deeper, go to my website. We've actually just given a tutorial on this, the 3-hour version at Rexus yesterday. The slides are already up. The video should be up soon as well. All right, thank you very much.